Okay, hello and welcome back. In this video, we're covering section 9.3 on the complex plane, mostly looking at complex numbers and how to convert them into a polar and exponential form. And that leads us to something called DeMoivre's theorem, which we will explain once we get there. So we'll start with just plotting points in the complex plane, looking at what a complex number would look like. Then we'll be converting that into between rectangular and polar form and exponential form. Then we'll find products and quotients of complex numbers, so we'll work with the multiplication and division of those. That leads us to DeMoivre's theorem, and we'll finish by looking at finding complex roots using the polar and exponential forms. So first, let's just recall what a complex number is and what it would look like visually. So this is plotting points in the complex plane. So you may recall working with imaginary numbers in maybe college algebra, where you had I, which was the square root of -1. More generally, when we say a complex number, that's something like 3 plus 2i, something that has some real part and something that's imaginary because it has this I value attached to it. And they're usually in a pair like this with some real part and an imaginary part. So let's be more general. Let's describe in general what a complex number would look like. So we usually use the letter Z to denote a complex number. And we can write it as x plus yi, where the x is your real part and the yi is your imaginary component. And if we're going to plot this, we can basically plot it as if we're in just the regular rectangular xy plane and we're plotting the point x comma y, like disregarding the I and just seeing it as a coordinate point. But technically we're going to be going into the imaginary axis, also known as the complex plane. So it's the plane in which complex numbers exist. So instead of x and y, we'll call this the real axis, and we'll call this the imaginary axis. But we can essentially treat it like the x and y axis. So if we're plotting some point, say this is the point z, which we're describing as x plus yi, then we would just go out a distance of x on the real axis and then a distance of y on the imaginary axis. So it is just like plotting a regular point, but technically we're on a different plane here, going into the imaginary plane. And we can build a triangle out of this, and there's another term that's introduced called the magnitude or the modulus of a complex number, which is essentially the hypotenuse of this triangle that's formed. And the symbol we use for that is, it looks like the absolute value of z. So we use that same notation. And this is just a distance of x, and this is a distance of y. So we have a formula for the magnitude of the complex number, which comes from the Pythagorean theorem. It'll be the square root of x squared plus y squared. So we see a lot of returning themes that we saw with polar values, and we'll be converting this into a polar form as well. Imagine this angle that's producing it. And we had called this r in polar coordinates, but in this rectangular complex plane, we would call that the magnitude of z, the magnitude of the complex number. So the text gives this definition. Suppose z equals x plus yi. It's a complex number. Then the magnitude, or they also call this the modulus of z. And there's our notation. Looks like the absolute value is the distance from the origin to that point. And here's our formula. It's again the Pythagorean theorem showing up. So let's just plot one of these points. So they give us this complex number, the square root of 3 minus I. So the square root of 3 is our real part. We can call that our x. And the imaginary part is just the number that's in front of I. In this case, it's a -1. So we can treat it like we're plotting the point root 3 minus 1. So if this is our real axis, and this is the imaginary axis, root 3 is like a little bit between 2 and 3. So I'd go that distance in the real direction, and then -1 in the imaginary direction. So somewhere roughly down here. So that will be our point, call that z, which is root 3 minus I. So let's convert now between this rectangular form and polar form. So it will follow a lot of what we've done in our previous videos. So let's just show the rectangular form again. That's z equals x plus yi, and we have the magnitude of z being the square root of x squared plus y squared. Well, we had some conversions previously between rectangular form and polar form. We had said that x equals r cosine theta, y equals r sine theta, and r equals the square root of x squared plus y squared. If you need to go back and review that, we go over this in the polar coordinates video, which was I think 2 ones previous to this. But just to quickly recap where that's coming from, if we have our complex number plotted here, and this would be the magnitude, or just that distance from the origin to the number. This is our y distance, and then this would be our x distance. And this is the angle going from the, in polar form, we'd call that the polar axis up to our, where our point exists. So we can say that the, like the cosine of this angle theta would be x, and we were calling this hypotenuse r. So x over r, if you multiply the r over, we get that statement, x equals r cosine theta. And y equals r sine theta if we take the sine of this angle. So let's convert the rectangular form to polar form. So I can say z, instead of x, I'll swap that out with r cosine theta plus yi. So y is r sine theta. This is multiplied by I. Maybe I'll stick that in parentheses. Well, each of these terms has an r, so we typically factor that r out in front. So I can say r times the cosine of theta plus, and usually put the I first, I sine theta. And then notice the magnitude of z in rectangular form is the same thing as r in polar form. So we can just say magnitude of z is equal to r. That distance from the origin or from the pole to the point. So this will be our conversion. In polar form, we can say z equals r times cosine of theta plus I times the sine of theta. In a lot of texts, this will be abbreviated, this cosine plus I sine. I think people get tired of writing all of that out, so it's often abbreviated as cis theta, CIS theta. That's cosine times I sine, CIS. So we could abbreviate this as Z equals R cis theta. I think that's mentioned kind of offhand in our text, and they usually work with the more expanded version. So we have basically what we went through here. So our polar form of a complex number. There are some conditions, so I just want to point out that R is positive or equal to 0, basically non-negative, and theta is between 0 and 2 pi. So that will show up for us in a little bit. So we can say the complex number x plus yi can be written in polar form as r times cosine theta plus I sine theta. And also that statement that the magnitude and our r value are the same thing. Main thing to remember is this first one here. We'll be using that a lot. The text introduces what's called Euler's formula. And we're kind of just told to believe this. The proof isn't given. It requires some additional skills that we've yet to achieve. So it gives us another expression, and this will be our exponential expression for a complex number. So this identity, e to the power of I theta, is equal to cosine theta plus I sine theta. And so since we were saying before a complex number in polar form was r times cosine plus I sine, using this identity we can say that z, the complex number, can be expressed as r times e to the power of I times theta. So this is another useful form. So this is our exponential form. So we have rectangular form, exponential, and polar, and we can transform between them. So let's get some practice working with these three different forms. So in example 2, we're given a rectangular form, root 3 minus I, and it wants us to express this in polar and exponential form. So let's first identify what x is. X is root 3. Y is negative 1. This was the point that we plotted earlier. Oops, not negative I, negative 1. It's just the number in front of the I. And so if we want to convert to polar form, we will need an r value and a theta value. So let's recall that in converting between rectangular and polar, r is equal to the square root of x squared plus y squared. So we'll be able to figure that out. And then in our polar coordinate section, we found theta often by saying that the tangent of theta is equal to y over x. And we had to consider what quadrant we're in order to get our correct angle. So just to make a quick note, if I'm imagining plotting this point, x is positive, y is negative. So we should be in quadrant 4. We're basically looking at this kind of triangle. This would be root 3, this would be negative 1. We can find our r value, and we're in quadrant 4. So with this in mind, let's try to do some conversions. So to put it into polar form, I need to find r. So r would be the square root of x squared plus y squared. So root 3 squared plus negative 1 squared. All of that under a square root. That will become 3 plus 1, or the square root of 4, which is equal to 2. So in this case, r equals 2. And then tangent of theta, we can say is y over x. So negative 1 over the square root of 3, or negative root 3 over 3. So that's going to be the pi over 6 angle in quadrant 4. I'll just make a note. Theta is in quadrant 4. So that means it should be 11 pi over 6. So we have our two components. You'll just box them out just so I can pick them. So let's put it into polar form. Polar form was z equals r times cosine theta plus I sine theta. So let's just plug everything in. We can say z equals 2 times the cosine of 11 pi over 6 plus I times the sine of 11 pi over 6. So that's the polar form of our complex number. And then let's put it in exponential form. So we said a little bit earlier that z can be expressed as r times e to the power of I theta. So that means our exponential form should be z equals 2 times e to the power of I times 11 pi over 6. So once we find r and theta, we just need to plug into the respective formula, depending on if it's asking for polar or exponential form. All right, in example 3, we're given a number in polar and exponential form, and they want us to convert it to the rectangular form. So they're starting us with z equals 2 times the cosine of pi over 6 plus I times the sine of pi over 6. So to convert this into rectangular form, we basically just need to evaluate everything. Like we can say, oh, the cosine of pi over 6, that's the square root of 3 over 2. And the sine of pi over 6 is 1/2. So distribute that 2. It's going to cancel with the 2 in our first term and also with the 2 on our second term. So we get the square root of 3 plus I. Notice that's now back in rectangular form. Just need to evaluate. So in terms of our polar coordinate, I know it wasn't asking for this, but just to compare the two. Our polar coordinate is r theta, so the r value was 2, and theta is pi over 6. Our rectangular coordinate, we can treat it as root 3 positive 1, with that 1 going into the imaginary axis, into the complex plane. So they want us to plot this. So root 3 between 2 and 3, and then positive 1. So we'll be somewhere over here. And again, this is the real axis, and this is the imaginary axis. But main point thing here, the main point here is that to convert from a polar form to rectangular form, just evaluate your cosine and sine expressions and then distribute that outer term. All right, so a big part of this section is starting to build up some operations using these complex numbers. So we want to define how we can multiply and divide them, how to take powers with them, and how to take roots with them. So let's imagine how we would multiply two complex numbers. So I can say we'll have one z1. We'll just call that r1 times e to the power of I theta. So that's in the exponential form, and this would be theta 1. So from our first point. And then let's just create some general second point. I'll call it z2. This would be r2 times e to the power of I theta 2. So we have two different complex numbers. So let's find out, using some rules of exponents, what a multiplication and division of these would be. So I can say z1 times z2. Well, this would be r1 ei theta 1 times r2 times e to the power of I theta 2. Make that look more like a 2. So this is all multiplying together, so we can put the r's together, r1 times r2. Then we'll be multiplying e to the power of I theta 1 times e to the power of I theta 2. So they'll have the same base. They both have the base of e. And then recall, with rules of exponents, if you multiply two things that have the same base in different exponents, we end up adding the exponents together. Just like if you're multiplying x squared times x cubed, the result would be x to the 5th power. So that same idea is applying here. We'll just add these two exponents together. I theta 1 plus I theta 2. And then we can factor that I out to express it a little bit more nicely, I suppose. So we can say z1 times z2 would equal r1 times r2 times e to the power of I theta 1 plus theta 2. Notice we add the angles together. So the r values multiply and the angles add together. And we can express this also in polar form. So z1 times z2 would be r1, r2, so the r's multiply. And we get cosine of the angles added, theta 1 plus theta 2, plus I times the sine of the sum of the two angles, theta 1 plus theta 2. So we have one expression in exponential form and one in polar form. But notice the general pattern. When you multiply two complex numbers, the r's multiply and the angles add. And it's coming from rules of exponents. So let's do the same thing with a division. So let's imagine z1 divided by z2. So in exponential form, that would be r1 times e to the power of I theta 1 over r2 times e to the power of I theta 2. So we can bring the r1 divided by r2 out in front. And then if you recall, if we had something like x cubed over x squared, two bases are the same in different exponents, you would subtract the exponents. This would be the x to the power of 3 minus 2, or x to the 1st power. So that same rule will apply here as well. We can reduce this to e to the power of I theta 1 minus I theta 2. And then we can factor that I out again like we did last time. So let's build our exponential form. z1 over z2 will equal r1 over r2. So we divide the r values, and then we subtract the angles. So theta 1 minus theta 2. And then we can make an equivalent polar expression. So z1 over z2 will equal r1 over r2 times the cosine of the difference of the two angles. theta 1 minus theta 2 plus I times the sine of the difference of the two angles, theta 1 minus theta 2. So there's our exponential and polar form of a division of two complex numbers. So just notice the general patterns here. When we multiply two complex numbers, the r's multiply and the angles add. When we divide two complex numbers, the r's divide and the angles subtract. So multiplication, addition, division, subtraction. So in the book, they just show the exponential form of this. Multiplication, multiply the r's, add the angles. Then division, divide the r's, and subtract the angles. So let's put this into practice. Let's see a couple examples. So we're given two complex numbers. They don't call it z1 and z2, just z and w, which makes it a little bit nicer to distinguish. So z is 3 times the cosine of pi over 9 plus I times the sine of pi over 9. And w is 5 times the cosine of 5 pi over 9 plus I times the sine of 5 pi over 9. And it wants us to find z times w and z divided by w, and it wants the answers in polar and exponential form. So for part A, let's find z times w. So we will multiply the r values, so that'll be 3 times 5. And then we will add the angles together. So let's put this into polar form first. So this should be the cosine of pi over 9 plus 5 pi over 9 plus I times the sine of pi over 9 plus 5 pi over 9. So let's just simplify that a bit more. This will be 15 times the cosine of 6 pi over 9, which that would reduce to 2 pi over 3. So 2 pi over 3 plus I times the sine of 2 pi over 3. So that's our polar form. Now let's write it in exponential. So that's r, or the multiplication of the two r's, so 15 times e to the power of I times the sum of the two angles. So we already have the 2 pi over 3 ready to go here. This will be our exponential form. So we multiplied the r's and added the angles. So let's find the division. Part B wants us to divide z by w. So that means we will divide the r values. That was 3 and 5. This will be 3 divided by 5. And then we'll subtract the angles. So times cosine of pi over 9 minus 5 pi over 9 plus I times the sine of pi over 9 minus 5 pi over 9. So what would that new angle be? Pi over 9 minus 5 pi over 9. Notice we get a negative angle, negative 4 pi over 9. And we need theta to be between 0 and 2 pi. If you remember, that was one of our conditions when we were setting this up. So To find a positive angle, let's just add 2 pi to this. Negative 4 pi over 9. Let's find the next coterminal angle. We can write that as plus 18 pi over 9. That's 2 pi. So 18 minus 4 is 14. So a positive 14 pi over 9 should be our angle that we should use. So that means we should get 3 over 5 times the cosine of 14 pi over 9 plus I times the sine of 14 pi over 9. So that's our polar form, and then as an exponential, it would be 3 over 5 times e to the power of I 14 pi over 9. The last note here, they just mentioned that the argument of a complex number is periodic, and we basically use that in our argument here since we had originally it was going to be a negative number, but we add 2 pi in order to meet the conditions. So that's what it's saying here. If you have some complex number, this is written in exponential form, and you add 2 pi or any multiple of 2 pi to the angle, you get an equivalent value. So just the same idea of like coterminal angles, but this will become important whenever we're taking complex roots. We'll have to use this. We'll have to use this idea, but we'll see once we get to that section. So we've multiplied two complex numbers together. We've divided them, but there's a couple more operations we could have. We need to also be able to raise them to some power, and then we'll take some roots as well. So let's imagine raising things to some power. So again, let's start with our complex number z, which we can express either as r times e to the power of I theta, or equivalently in polar form as r times the cosine theta plus I sine theta. So let's say we want to raise it to some power, z to the power of n. Well, let's take the exponential form. This would be r times e to the power of I theta raised to the power n. The r and the exponential are multiplied inside the parentheses, so we can distribute this power. This would be r to the power n times e to the power I theta to the power n. And then recall, if you raise a power to another power, if we add like x squared cubed, the powers multiply. This would be x to the 2 times 3 power, or x to the 6 power. So that same property will apply here. So that n will multiply into that exponent. So we can say z to the power n would equal r to the power n times e to the power of I times n times theta, or we can say I times n theta. Notice the angle will get multiplied. And then we can expand this as polar form, so r to the power n times the cosine of n theta plus I times the sine of n theta. So again, we have an exponential and polar expression. And here, so we're saying if we raise a complex number to some power, the r value gets raised to that same power, and the angle gets multiplied by whatever that power number was. If it was like to the third power, we would multiply the angle by 3. So this is DeMoivre's theorem. If z is a complex number, and they show it in exponential form, then we get our exponential definition. R gets raised to the power of n, and the angle gets multiplied by that power, where n is an integer, and it's positive. So let's get some practice raising a complex number to some power. So we want to express this in exponential form and in rectangular form. So we're taking 2 times the cosine of pi over 9 plus I times the sine of pi over 9. That's like our z, and we're raising it to the third power. So if we express this in exponential form, that would be 2 times e to the power of I pi over 9 raised to the third power. So the 2 will get raised to that third power. And the angle gets multiplied because we're just applying this rule of exponents, pi over 9 times 3 over 1. So we end up with 3 pi over 9, or that would turn into pi over 3. And then 2 cubed is positive 8. So 8e to the power of I pi over 3, because it wanted it in exponential form. We could expand this into polar form if we wanted to. We would raise that 2 to the third power, and you would see the pi over 3 inside of the cosine and sine. And it also wanted it in rectangular form. So let's actually do that expansion. That was our strategy. If we expand this out and just evaluate everything, then we can convert it into rectangular form. So this is 8 times the cosine of pi over 3 plus I times the sine of pi over 3. So the cosine of pi over 3 is 1/2, and the sine of pi over 3 is the square root of 3 over 2. So let's distribute that 8. 8 times 1/2 is 4. So 4 plus, we'll get another 4 root 3, and we can place the I on the back. So 4 plus 4 root 3i. That'll be our rectangular form. All right, let's look at our next example. So we want to express 1 plus I to the 5th power in exponential form and in rectangular form. So that means our complex number is what's inside there. We can say that z is 1 plus I. This is in rectangular form. We could maybe brute force this and just multiply this by itself 5 times. 1, 2, 3, 4, 5. 1 plus I. But we'll see if we're working in polar form, it becomes a bit easier. So let me rewrite this again. 1 plus I. So we want to get it into polar form so we can apply that theorem. So we need an r value and a theta value. So this means that x is 1 and y is also 1. They're both positive, so we should be in quadrant 1. R is the square root of x squared plus y squared, so 1 squared plus 1 squared. So that means r is the square root of 2, so we'll hang on to that one. And then the tangent of theta is y over x, so 1 over 1, which is 1. Well, the angle in the first quadrant that has a tangent of positive 1 is pi over 4. So we'll need that piece. So that means in exponential form, our complex number is the square root of 2 times e to the power I pi over 4. So that can be our starting point. So when we're saying we want to take 1 plus I to the 5th power, we can express that in our exponential form as the square root of 2 times e to the power of I pi over 4 to the 5th power. So the root 2 will be raised to the 5th power. We'll think about what that is equal to. And the e to the power I pi over 4 will be raised to the 5th power. The square root of 2 to the 5th power, what would that be? Well, that's like the square root of 2 squared times the square root of 2 squared times the square root of 2. 2 plus 1 gives us our 5th power. And both of those squares will cancel, so we end up with 2 times the square root of 2, or 4 root 2. So that means this should give us 4 root 2 e to the power, and the 5 will multiply into the exponent, so I times 5 pi over 4. So there's our exponential expression. But let's convert it back to rectangular. So we can expand this out. 4 root 2, this will be times the cosine of 5 pi over 4 plus I times the sine of 5 pi over 4. And then let's evaluate. So 4 root 2 cosine of 5 pi over 4. That is over in the third quadrant, so the cosine is negative root 2 over 2 plus I times the sine of 5 pi over 4, which is also negative root 2 over 2. And then let's just distribute that 4 root 2 in. The 4 is going to get reduced by these 2's in the denominator. Let's see, and also the root 2 will multiply with the root 2's. So maybe let's write it like this first. Let's keep the 4. And let's just cancel the roots first. So this will be like 4 times negative 2 over 2. Since the root 2 times root 2 gives us a 2 and we have a negative, the same thing will happen to the second term. So we can say 4 times I times negative 2 over 2. So those will just become negative 1's. So that means we should have negative 4 minus 4i as our rectangular value. So now we've multiplied complex numbers, we have divided them, we've raised them to some power. So now let's find some roots. So we can imagine taking, say, like the nth root of our complex number z. Well, remember, we can express a root using a fractional exponent. Like if I had x, the square root of x, we can write that as x to the 1/2 power. In general, if we have the nth root of x, that would be x to the 1 over n power. So let's apply that same idea. We can write this as z to the power of 1 over n. In exponential form, that would be r times e to the power of I theta to the 1 over n power. So we can distribute the power. This is r to the 1 over n power times e. Now this will be, we can express this as I times the power of theta over n, because it'll get divided by the n. We can bring the I out in front. So notice the angle gets divided. And here we actually, it becomes a little bit more complicated. We'll end up with multiple solutions for these roots. Recall earlier that we said we could add 2 pi to our angle and get another solution. So we can do that here. We can write this as r to the power of 1 over n times e to the power of I, and we can say like theta plus 2k pi over n. So like plus any multiple of 2 pi, meaning like coterminal angles. So let's write this out a little bit differently. The r to the 1 over n power, we can express that as the nth root of r. So we apply the same root to the r value. And then this would be e to the power of I. And I like to write this, like I like to split up this into 2 different fractions. So like theta over n, we divide the angle by n, and then plus 2k pi divided by that same n. So kind of like if you recall solving a trig equation, we got some general solution involving coterminal angles. So we can split this up into, so this would be the exponential form. Let's express it as the expanded polar form. So the nth root of r times the cosine of theta over n plus 2k pi over n. So this is like a general solution, plus I times the sine of theta over n plus 2k pi over n. And the number of solutions that we'll get will be the same as the index of this root. So the way to express this in this general form would be to say that we're going to take a k value of 0 first to get our first solution. So we did that when we were solving trig equations. And then we take a k value of 1, and then 2. We basically do this until we get to k minus 1. What this means is if this was, say, like the third root, we would take a k value of 0, 1, and 2. We'll still get 3 solutions, but we stop at 2. We don't go up to 3. We're basically just starting to count at 0 instead of counting at 1. So this will make a bit more sense when we see a specific example. But here is our general exponential and expanded polar solution. So it's still following this theme where like the operation that's happening happens to the r value. So we take the nth root of our complex number. The r value will also be hit with that same root. And then the angle is divided by n, but then we also get multiple solutions. We get this coterminal general solution. So let's see an example. And that's what it's writing out here in the text theorem. So they are taking a root, so the nth root of our r value. They're writing this a little bit differently here, but there's our division by n, and then there's our angle with all coterminal angles. So I'm basically distributing that 1 over n to both terms. So let's find in example 7 the complex cube roots of -1 plus root 3i. So I'll start out by saying that that's our complex number, -1 plus root 3i. Let's get it into exponential form. So our x value is -1. Our y value is the square root of 3. X is negative, y is positive. That means we're in quadrant 2. R is the square root of x squared plus y squared. So -1 squared plus the square root of 3 squared. Well, that'll be 1 plus 3. So r is equal to the square root of 4, which is 2. We have an r value of 2. Tangent of theta is y over x, so root 3 over -1. That's negative root 3. So this will be the pi over 3 angle in the second quadrant. That means theta must be 2 pi over 3. So our complex number in exponential form is 2 times e to the power of I 2 pi over 3. So we'll start there. So we want to find the cube roots of this complex number. So we're finding the cube root of z. So that means we can say this will be 2 times e to the power of I 2 pi over 3 to the 1/3 power. So that means we'll end up taking the cube root of 2. So the r value gets the root. And then we can express this as e to the power of I times our angle divided by 3. So 2 pi over 3 divided by 3 plus 2k pi also divided by 3. And we're going to want to find k values of 0, 1, and 2. So we stop right before 3. We still have 3 values, but we start counting at 0. So let's just simplify what's in that exponent a little bit. So this will be the cube root of 2 times e to the power of I times, that looks like it will be 2 pi over 9. And let's get a common denominator here. 2k pi over 3, we can express that as 6k pi over 9, since we're going to be adding this to our 2 pi over 9. So I just multiplied the top and bottom of that fraction by 3. So we get 6 on the top and 9 on the bottom. So let's start listing out our solutions. And we want the solutions in exponential form. So our first one, we can call that z0. That'll be when k is equal to 0. Basically just our first 2 pi over 9 inside. So square root, or cube root of 2 times e to the power of I 2 pi over 9. Plus 0 technically. I guess I can write that out. So cube root of 2 times e to the power of I 2 pi over 9. All right, let's find our next root. So this will be cube root of 2 times e to the power of I times 2 pi over 9 plus our first 6 pi over 9. So we'll just be adding 6 pi over 9s each time. So that looks like 8 pi over 9. So this would be cube root of 2 times e to the power of 8 pi over 9. And then our next one, let's take that previous 8 pi over 9 and add another 6 pi over 9. So cube root of 2 times e to the power of I times 8 pi over 9 plus another 6 pi over 9. So 8 plus 6 is 14, so our third root should be cube root of 2 times e to the power of I times 14 pi over 9. And those will be our three solutions. Remember we stopped counting at 2 here. So if it was the fourth roots, we would have one more. We would just keep going until we hit the correct number. Alright, so that's it for this section. So we plotted points in the complex plane, converted a complex number between rectangular form and polar form and exponential form. We found products and quotients, so we multiplied and divided them. We used DeMoivre's theorem, so that was raising a complex number to some power. And then we took roots and we found complex roots. Okay, that's it for this video, and I'll see you next time.